Okay, now once you are done with your thermal design philosophy, you need to analyze your design whether it's able to match your requirements, whether all the components stay in the operating temperature limits throughout the mission. So you run, you make these, you develop these models to ensure during the all phase of the mission, your spacecraft is at optimum temperature limits. Now, there's a geometric mathematical model and there's a thermal mathematical model. So geometric mathematical model is basically the discretized domain, which you have heard in this term you have heard in CFD also. So you take the CAD, you break the CAD into discrete elements, and you solve the equations, your thermal equations, basically the uh, your Stephen Boltzmann equation, your calculation of the view factors, and your calculation of the Fourier's equation, Fourier suite equation at every node. So geometric mathematical model is essentially uh, the surroundings of the spacecraft, which is exchanging heats within itself, within its uh, surfaces. For example, if you have a rover or a spacecraft, you need to ensure that your model have all these important wall surfaces, and the components which are exchanging heat within themselves. Now, you need to specify the materials and the optical properties in the geometric mathematical model. Then comes your thermal mathematical model. So thermal mathematical model is basically a network, resistance network for all these surfaces which have some material properties and optical properties. Now this network of conductances is made using the simulation objects, as we call it in these softwares. These are called simulation objects. For example, you need to connect one surface to another with heat transfer coefficient. So based on the empirical relations and the area of contact from your CAD, you are able to determine what kind of contact conductance will be there between these two surfaces. So like this, you make a network for all of these components, basically whether they are bolted, whether they are glued, or whether they are welded. You came to uh, a contact conductance calculation and you enter it in the model. Then you define the loads on your electronics. Basically, all the electronics we use on the spacecraft, they are not 100% efficient. Means they dissipate some amount of heat, which is around 20% for most of the components. But for components which, for example, I told about the power distribution units. Power distribution units needs to change the voltage from high to low and low to high, which dissipates a lot of heat. And these are very less efficient, and most of the power goes into heat dissipation. So you need to put a number on the heat dissipation. What is the amount of heat these electronics are expected to dissipate during your mission. Now, once your this is made, network of the conductances and the boundary conditions, that what will be the environment, how your sun rays will be falling on the model. So basically, in these softwares, you have a provision to model the orbits also, which means you can be enter the data for your inclination of the orbit, what will be the sun azimuth and elevation. Based on that, it will calculate what part of the your satellite or the spacecraft will be illuminated by the solar rays, and depending upon that, it can calculate the heat loads on the spacecraft and give you the temperatures as a output on each of the element of the model. So there are some softwares which are used for this purpose, that is FEMAP TMG. It is a software from NX, and FEMAP is basically a structure software which have a module called TMG, Thermal Model Generator. Then we have NX Space Systems Thermal, which is widely used commercially in many companies. Then we have Thermal Desktop, which actually mostly used by American companies. And then we have ESA 10. ESA 10 is basically a proprietary software for a European Space Agency. They use this software for their design and analysis. So that's how you reach the temperatures, operating temperature which you require for the mission. You are using these softwares, you are able to exactly input your heat load, your contact conductances, and the boundary conditions in which your spacecraft will be facing during the mission. Now, after this analysis, you need to verify and validate whether the thermal design you have expected is achieved or not. Now, verification and validation are two different things. So, verification is basically whether you have developed the product in a right way. So, this is now again verified through simulations, like I said, for using these softwares, and it is done through various tests during the development process itself. So those are called development tests sometimes. Then we have a validation. Now, validation of a system refers to whether you have realized the right product, whether it is giving you right performance as required by the stakeholder or the someone who is the end user. So this validation is very comprehensive, and they are done using a uh, system level thermal test. Now these tests are performed in vacuum chambers. So basically, two tests are there which are very essential for validation of the thermal performance of the spacecraft. One is the thermal cycling test, and another is the thermal vacuum test. So thermal cycling test is basically done in uh, normal pressure, and you just take the spacecraft at specified temperatures, higher temperature and lower temperatures. Now the purpose of this test is to find out if there is any fault during the workmanship, during the manufacturing process, or during the design process. So basically, you qualify your system using the cycling test for a specified temperature range. Now then comes the thermal vacuum test. So thermal vacuum test, we do in the thermal vacuum test, we do thermal cycling also and thermal balance also. Again, the thermal cycling test which I talked earlier, it was done at normal pressure, but the thermal cycling which we'll be doing in the vacuum chamber will be done at very in the vacuum, so which is around 10 raised to power minus 6 or relatively means as compared to the deep space pressures. Now, during this vacuum test, we try to emulate the same environment which we are going to anticipate for the mission. So, like in the cycling test, thermal cycling test, since it was done at the normal pressure, it was easy to increase and decrease the temperature at very high rates. But due to the vacuum, only the radiation and conduction mode of heat transfers are present. It takes a lot of time for a satellite to reach the equilibrium for high temperatures as well as low temperatures. So for the vacuum test, which could last maybe for small satellites, it easily lasts for 15 days. So there's a 15 days of work shifts, continuous work shift to monitor the spacecraft. So in the vacuum test, first we do thermal balance test and then we go for the cycling. In the thermal balance test, what you do is you take one activity of the spacecraft operation and let the temperature come into equilibrium with the environment. So this thermal balance test is actually helps in correlating your thermal model which you have made earlier. Now, because of the uncertainty in the conductance values and the loads on the electronics, you are able to this cannot be same at the time of testing because the numbers you have put during your thermal modeling, they are not very accurate. You can only get the right number while doing the testing. So after the testing, you come back to your model and you correlate with the test results. So now you put in your model the actual heat dissipations on the electronics components and try to correlate your model so that when your spacecraft in the mission after the launch, you will be able to predict the temperature of the spacecraft using your model for any situation. So, which is the purpose of the thermal balance test to correlate your thermal model. So, after this testing is done, there are multiple reviews. For example, flight readiness review. The review board will actually qualify if your spacecraft is worthy of flight or not, depending upon the all the test, not just the thermal test, all the tests which are which has been performed on your spacecraft. So with all this testing covered, now we'll look at a small case study and we'll try to find out how a thermal control or a thermal design of a Chandrayaan 2 would have been evolved. So first, these are the design inputs for starting the design of a spacecraft. So first you need the mission profile. So for example, if we see here, this is the mission profile for the Chandrayaan 2. Now we can see these pink line shows the orbits of the Chandrayaan 2 around the Earth. In the center, we can see it's a blue dot which is representing the Earth. Now we know that there are Earth orbits, then there's a lunar transfer trajectory, and after that, after the spacecraft reaches the sphere of influence of the moon, it get pulled by the gravity of the moon, and then there will be orbit of moon. So this is the mission profile. So at these different orbits, there are different environmental conditions which is need to be analyzed as a mission input, as a mission profile. Similarly, the attitude and orientation of the spacecraft during the mission phases. It is this is the another input. So what would be the orientation of the spacecraft or the attitude of the spacecraft is important, because during your analysis you need to know from uh, which side is getting heated through sun, and which is the other side facing the shadow, from where there'll be a uh, heat rejected from the spacecraft. So this is another input which is required. Then we need to know the temperature limits for all components. So what happens, there are components which have different temperature ranges. For example, your communication systems, they normally operates in the temperature range of -20 to 55 degrees Celsius. Your battery have a very narrow range, +5 to 20 degrees Celsius. Your solar panels, on the other hand, have a very wide range. It can withstand -100 degrees Celsius to +100 degrees Celsius. Then there are other components, other electronics, most of the electronics which can work in -40 to +85 degrees Celsius. So all these temperature limits you need to know in your spacecraft before doing the thermal design and analysis. Then there are some components which have a requirement on the gradient. Otherwise, they will tend to fail. So for, let's say, the battery pack, there's a gradient requirement that no two cells of the battery must be, the temperature of no two cells of the battery must be greater than 3 degrees Celsius. So this is the kind of gradients requirements we have on the battery. Then we need to know the power dissipation of all the components. For example, there is a S-band transponder which is dissipating X amount of heat, but this transponder may not be working at all the time. So either you design your simulations so as to account for these times when it is on, when it is off, or you take a average of these numbers for your thermal design purposes. That is one approach. Then it is important to know what are the material which is being used in the spacecraft and their optical properties. So most of the times for the passive thermal control, your the designer will tend to use the passive thermal control, the properties of the surface, optical properties of the material itself, to reach the adequate thermal control. So all these inputs are required for from the thermal design point of view before you start for the thermal design. Now, if we come to this Chandrayaan-2 profile, there were 6 orbits before it reaches to the lunar transfer trajectory. So if you see, these 6 orbits are basically Earth centric. So when your spacecraft in this orbit, in Earth orbit, it will have a sun load, which is the solar flux from the sun, which is maximum around 1420 watts per meter square. Then there will be a earth shine. Earth shine is basically the heat load due to the temperature of earth. On an average, it is around 236 watts per meter square, which is based on the average earth temperature, which is around -18 degrees Celsius. Then what sunlight you receive from the sun, it also get some of it gets reflected back to the space. So during the geocentric orbits, when Chandrayaan is orbiting the Earth, the Chandrayaan was facing this Earth albedo also, which is 0.3. means that 30% of the solar flux which is uh, deflecting back to the space is encountered by the Chandrayaan 2. Then, if you see this, sorry, long orbit, which is called a lunar transfer trajectory, which is also a Earth-centric orbit, when it reaches to a particular height from the lunar surface, which is around 60,000 kilometer, it is said that it has now reached to the sphere of influence of the moon. So then there will be another maneuver which is called lunar orbit insertion or lunar orbit capture. At this point, your spacecraft will start rotating in the lunar orbits, in the orbits of the moon. So while it is in the lunar orbits, there are other loads which is coming from the moon. So sun load will be there continuously. It will be 1420 maximum watts per meter square. Then there will be a moonshine. Now, as I told earlier, moonshine means this is the load which is due to the uh, which is due to the temperature of the sun itself. Now, at this point, when your spacecraft is between the sun and the moon, it will face the situation like there are two suns heating the spacecraft. Now, while your spacecraft goes to the dark side of the moon while orbiting, there's a flux of only 6.5 per meter watts per meter square. And moon albedo, which is the reflected light from the sun, is around 0.07. Now we have the thermal loads which are on the spacecraft. We have seen that while spacecraft is orbiting the Earth, there will be environmental loads, which is sun load, earth shine, and earth albedo. In addition to that, there will be a internal dissipation because of the operation of the components, and there will be another load because of the very low temperatures of the deep space environment, which is around 4 Kelvin. So you use all these conditions and put it in your software, and you come to the uh, temperatures, and with the thermal design philosophy, you'll be able to optimize your thermal design, whether what will be the radiator size, what will be the surface finishes you will be using for different components. You'll be able to get the results for different phases of the mission. So now another phase of the mission is the landing, which we are not going to talk because it involves different problems of its own, because it's not a orbit anymore. And generally these softwares are not able to model the thermal simulations, to model the landing scenarios, basically, in which the altitude is always decreasing. So there are some ways to do it, which we cannot talk in this webinar. So this is how the Chandrayaan 2 faces all its heat sources, and what are the thermal loads. This is the first step for starting the thermal design for the Chandrayaan 2. Now coming to the state of the art basically is the present level of the technological readiness. Now for the MLIs, so there are 9 levels according to NASA, from TRL level 1 to TRL level 9. So TRL1 means basic principles are observed and they are being reported. And the TRL9 means the actual system are flight proven and they have done successful missions operation. So for the multi-layer insulation, it is already a TRL level 9, which means it is already very mature technology. Similarly, the thermal coatings and paints, they are also matured and have TRL level 9. Deployable radiators is something which are in the prototype stage, and these prototypes have been demonstrated. So it comes under TRL level 7. Similarly, for the heat switches and the looped heat pipes and heat switches are also, their prototypes have been made and they have been demonstrated in the relevant environment. Louvers are one of the technologies which have, if you see here, they have flap kind of thing. On one side, it is a high emissive uh, coating, and on the other side, there is a low emissive coating. So whenever there is a requirement to switch from, let's say, you are at you are facing the sun and you want to absorb only a very less heat, so you face one side of the flap and reject most of the heat. On the other hand, let's say you are operating in a night time and you don't want to lose the heat, so you will have a other side coated with a very low emissive coating, and you will be able to retain the heat through this low emissive coating. So this technology is also at the prototype level, but it is not matured. The sun shield and the flexible thermal straps, these are also at TRL level 7, and they are in the stage of prototyping and not been, some flexible straps had been flown, but technology is still not matured. So coming to the career path and job opportunities, the if we talk about the small satellite market alone, we have seen that there is a growth from 2019 to 2021 of around $6.7 billion, which is a huge market. So to give you the perspective, we know that global space industry is going to reach USD 1 trillion by 2040, which is currently at 350 billion. So I just talk about the small satellite market, which is presently $9.7 billion out of USD $350 billion space industry. So there is a huge scope of expansion, and you will have huge opportunities in other sectors also, like maybe launchers or big satellites or other kind of deep space missions and interstellar missions. So what are the typical roles you will encounter is these are the typical designations basically. Thermal engineer or a spacecraft thermal engineer or spacecraft thermal analyst. If you look at if you try to search it on LinkedIn, you will find a lot of job opportunities around the world. Unfortunately, in India, the scope is still increasing, but it is good thing is it is increasing at very fast pace. Now we talk about the notable companies in India and abroad. In India, first name will come into mind is the ISRO. And one of the misconception is you need to have a aerospace degree if you want to enter aerospace domain, which is not true because we know that most of the engineers working in ISRO have mechanical degrees. So ISRO is one company where you can start your career. Of course, you have to write a exam for that. Then there are companies which are making small satellites for a specific mission, like Pixel. Then there is Team Indus, which is making lunar landers and lunar rovers. Then there are other small satellite companies like Kawai Space and Exceed Space, which are based in Mumbai. There are small communication companies which are making communication devices like Astrogate. Then there are companies which are making launchers, that is Skyroot, Agnikul. Bellatrix is one of the companies which has already demonstrated the electric thruster, Hall effect thruster. Then Alpha is Design is one company which is making the satellites. So if we talk about companies abroad, there are companies like iSpace from Japan, which is making the lunar landers and rover, which is a very big company and having headquarters in Luxembourg and USA as well. Then many of you must have heard of OneWeb, in which Bharti Mittal have taken some stake and they are making communication satellites. And there's a launcher company called Rocket Labs from New Zealand. They are making small satellite launch vehicles and they have already been launching many satellites. Then there are companies which this company Maxar Tech, it is making Earth observation satellites for imaging and data processing. It's a huge company. If you open your Google map, you will see that images are copyrighted by Maxar Technologies. Then everyone have heard about SpaceX, which is now a very huge company. Of course, it is difficult to get in companies like SpaceX because they are restricted through ITAR restrictions for Indians. But the other companies like iSpace, OneWeb, Rocket Labs, these don't have any kind of ITAR restrictions. You can apply and you may get lucky. Then another company, the Australian company is Space Machines. Australian space market is pretty opening up these days, and there are a lot of companies which are coming up in Australia. So Space Machines is one of that company, and there's a few other companies like Gilmore Technologies is also there. So I think I'll end this discussion